So welcome everybody to Code D. We are Detroit's computational design community. And this time due to COVID, we are now remote, and I think we've got a lot of people from all over the place. So we're a little bit bigger than Detroit. But just to give you a quick background of who we are and what we're trying to do, our mission is to really empower students and professionals in the AEC industry to learn, share, and implement new ways of thinking that are native to the digital age. So today that might mean Grasshopper or Dynamo. Tomorrow it might be AI, machine learning algorithms. It doesn't really matter. We're here to learn. And what's really important for us is not just to hang out here, learn from each other, but really is to implement it in practice. And to that end, in addition to the quarterly meetings we have, which are big forums, we have all different kinds of lectures and different discussion topics, but we also have a planning committee. And that's the group that curates what it is that we share every quarterly meeting. And I would just say to anyone on the call, if you're trying to push computational design at your firm, we want you to join this planning committee. This is where a lot of the real thinking happens. I really enjoy this group. A lot of side conversations occur that really upskill us. So if you're really trying to push this locally in your own office, you don't have to just be alone in the dark as one of the only people pushing this in your firm. There's a lot of us out here. Hence, we have a lot of people joining this call today, right? We're all interested in it. But together, we believe that we can change the industry. It might be hard to change your firm alone, but together we can really make a difference. And without further ado, the reason everybody is here, we are so excited to introduce Andrew Heumann, the Andrew Heumann, coming all the way from New York remotely to our Code D presentation. I'll let Andrew introduce himself, but from our perspective, Andrew is one of the top in the game. Really is a pleasure to have you here. So Andrew, would you mind introducing yourself?
Sure. Yeah. Thank you so much for having me. Thank you to Code D. Thank you to AIA Detroit. Thank you to you, Leland. And I also wanted to give a special shout out to Zuby, who invited me to join today and is unable, unfortunately, to join us for this. But he's amazing, and he's the reason that I'm here. So just really, really excited to be a part of this. I think it's really amazing that you guys are, kind of connecting with a larger group and taking advantage of this moment to, do something a little bit bigger. And I think it's amazing. So I won't do too much in the way of introduction because in a sort of long-winded way, my whole presentation is kind of like a long introduction. So I won't give too much detail, but my name is Andrew. I have been doing computational design in various forms since about 2008. And, I've kind of made a journey from being an architectural designer to being a software developer who's building tools that address AC. I don't think I'm going to say much more than that because I think the presentation actually sort of covers the narrative piece of it as well. But if there are more holes I can fill in later, we can have questions there at the end.
Can you share your screen, Andrew?
Yep. One moment. All right. Do we see that?
Perfect.
Okay. Awesome. So I know that this was originally billed as the future of collaboration, and I probably will touch on that a little bit, but I think it's going to be about a lot more than that. The thing that I am really passionate about and want to talk about with you all tonight is design tools. I'm really interested in how we as designers interact with technology. And this talk is going to be a very personal journey about, kind of how my thinking on this has grown and evolved over time. And at the end, I'm going to talk about Hypar, which is the company that I work for now, and kind of share how some of this stuff has shaped the ways that we're thinking about building the next generation of computational design tools. So this story actually starts in 2007. I was a first-year architecture student. That's me. In fact, my hair right now with COVID, because I haven't gotten a haircut in a long time, is starting to approach the volume it had at this moment in my life. It's a really good thing that this crappy picture I pulled off Facebook is so pixelated because you can't see that I have been crying from exhaustion and humiliation at not having finished this thing. So, you know, this was one of the first design reviews I ever had. I was just starting out, and you can see, it's probably a little hard to see, but we're all holding rocks. The design assignment that we had been given as first-year architects was to find a rock and then build this kind of like waffle housing for the rock. Like, build these sort of like flat slices out of museum board that would slot together in a way that would have sort of a carved out hole that would cradle the rock perfectly. And the reason I was crying in the previous picture is that I had stayed up all night cutting museum board with an X-Acto until my fingers were numb. And I had decided at 5:30 that morning that I was quitting architecture, that I was done with this. This is stupid. I can't believe they're having us do this. This is totally preposterous. And I got yelled at the review for not being totally finished. And I was really demoralized at this moment. So I even started going to transfer meetings to see if I could transfer out of architecture into like hotel management or engineering. And, you know, two lucky things were true at that moment. One lucky thing was that my school made transferring pretty hard. But the other, probably more significant lucky thing is that not long after this, McNeil announced a thing called explicit history, which very shortly thereafter got renamed to Grasshopper. And I was lucky to have, in the beginning of my second year, a professor named Dana Kupkova who kind of introduced our studio to Grasshopper. And Grasshopper literally changed my life. You know, it really blew my mind that you could build these amazing things. And in particular, something that stood out to me was that someone had already created a script that automated the very thing that nearly made me quit architecture. This is a script where, you know, you plug in a shape and it would slice it in perpendicular directions, calculate all of the slits, label all of the rows, and then lay them out flat for a laser cutter. And you know, this really left an impression on me. There's this crazy language you can learn, and it gives you these magic powers, and you never have to do something twice. You can build a tool and then reuse it over and over again. And so, you know, I ended up using Grasshopper on all of my student projects. I ended up pulling a lot fewer all-nighters. I even managed to graduate without changing majors. And after graduation, Grasshopper actually got me my first job working at NBBJ in Seattle as a junior designer. And, you know, I was working on design projects, but I was brought in specifically because I had some awareness of this brand new tool, Grasshopper. And I really wanted to bring this epiphany about the power of computation to bear on my professional work and on real practice. I wanted everybody to be as excited about the potential of not having to do everything twice and the potential of being able to automate the tedious parts of a process and, you know, not stay up until 5:30 in the morning manually generating CAD files or cutting things in real practice. And so I worked on projects where there was the opportunity to do that. And this is, I think, a pretty typical story of kind of the computational designer role that was starting to emerge at firms at that time. I was mostly deploying computation to solve complex geometric problems, doing design iteration and figuring out complex fabrication strategies for things like this ceiling. So, you know, this ceiling is this, you know, highly articulated 3D surface that gets produced out of these slats that hang. This is a lobby of a building called 2 Union in Seattle. And in fact, the script that I used for this project is really just an advanced version of that same waffle script that I found in college, where, you know, you take a freeform and you slice it and you come up with labels. You know, it was a little more advanced because it had to break things down into smaller parts and so on, but it was really the same fundamental concept. So I was really excited to be, you know, deploying these tools and then at the scale of like real, you know, the real built environment. The other role, and again, I think this is pretty typical of the kind of computational designer at a practice, is to be the sort of interoperability jockey, figuring out how to not just rationalize complex geometry, but also translate it from software program to software program. I think there are a lot of tools that do this better and better now, but at the time it was a little bit of the Wild West in terms of how you figure out how to get you know, your geometry out of Rhino and over to Revit and down into CAD and whatever needed to happen. So this was a workflow I actually made a little bit later on when I was working at Woods Bagot Architects. This is the Christchurch Convention Center in New Zealand. And, you know, the process was basically oriented around taking this design model, which was sort of a lightweight Rhino model, and figuring out how to document every last colored tile that had to be put onto this facade, every little offcut, all of the specific tiles so that it would have, you know, the right colored appearance and those sorts of things. So that was also a kind of typical job of the computational designer, is to figure out how to translate this stuff from platform to platform. And the other thing that I was doing with some regularity, again, fairly typical, is analyzing the performance of a project. So, you know, this is a lot of solar radiation studies with tools like Ladybug and Honeybee, or analyses of a more subjective nature, like these view studies that I did for Rainier Tower in Seattle. This is also a project that's built now. Interior studies that looked at things like visual connectivity, or even running detailed simulations of the behavior of occupants moving through space, for instance, to compare two different sites, as we did in this example. And so, you know, I think that the sort of two things that really were the sort of key, and I think remain a big part of computational practice, is one, being able to sort of generate solutions, you know, build a generative model that automates some process or automatically generates some form, and then being able to analyze it or measure its performance or see how it's doing against the goals that you've set for yourself. But in practice, there is a problem. And this is something that I, you know, faced from the very beginning, which is that these tools are fragile. They make it really hard to collaborate. And, you know, I was always striving to create useful tools that others in the practice could use. And yet, in reality, it always wound up being me who would run the script. This wasn't always true. NBBJ was actually pretty good in this regard, and so is Woods Bagot. But I think in general, this is a problem that the industry still faces. It's like, okay, you made the script. Now you are forever the keeper of the script. And not enough people were willing to learn enough Grasshopper to get in here and to operate this, or even just to use a tool that someone else created for them. So what I did at that time was I started developing a plugin for Grasshopper that was designed to alleviate that a little bit, that enabled Grasshopper users to build user interfaces for their scripts, precisely so that they could be shared with others in their practice. And so this is Human UI, which is a plugin that allows you to build these user interfaces just using Grasshopper components, but you could basically wrap your definition with a UI and share it with somebody. And that worked fairly well. I think, you know, we did a lot of that at NBBJ, and I went on to Woods Bagot and did a lot more of it, where we were building pretty sophisticated sort of mini applications that were all backed by a Grasshopper script. This one was designed to automate the process of generating like detailed Illustrator site models in New York. So we could pull in a bunch of CAD data, you could kind of pick all of the layers of analysis data you wanted to include, and you could hit export and it would spit out an Illustrator file with all of your layers already set up. And then you could just sort of turn layers on and off to get an entire set of diagrams. And, you know, I think one of the characteristics of this that made it amenable to automation was that it didn't actually have that much to do with a specific design project. It was a repeatable process that we were doing over and over again. Things always get a little more difficult when we wanted to apply this to a specific design project. So this is a Human UI that was created by my colleague Brian Ringley at Woods Bagot. And this was a tool that allowed various kinds of design studies for this tower project. And the cool thing about this was that you could make high-level decisions about massing and immediately see their downstream consequences for things like area targets, structure, constructability, you know, panelization, all of this stuff. But inevitably what would happen is that, you know, a designer is playing around with this, they're playing with the level of flexibility that you've given them, you've exposed as a UI, and then they want to do some other thing that the UI doesn't accommodate. And so I think this is always a trade-off when you're building parametric models, is figuring out, you know, how do I design this in a flexible enough way that it can accommodate future change? And I think it's actually really hard to do that with tools like Grasshopper. So just one more example of these, these kind of tools that we were building. I think at their best, what they can do is start to bring in the, oh, that's right, this video like never plays all the way. Oh, here we go. Bring in constraints of the problem. So in this case, this tool actually knows something about the zoning regulations on this specific site, and it can generate zoning compliant masses to do a feasibility study. And then you can link these possible formal configurations to analysis and see what the consequences are for views or for, solar impact or for overshadowing or whatever you care about. And so, I think this is a really exciting and useful way to work for practices who want to put their computational tools into the hands of more people in the practice without necessarily digging into the spaghetti. And the thing that's been really rewarding for me is to see what other people built with Human UI. So tools for massing studies, space planning, analysis, jewelry design. And the thing that I love about this is that people are really trying to craft their own intelligent design environments, spaces for them to do design work that have an inbuilt notion of both the constraints of a problem and the goals and objectives they're trying to achieve. And I think this idea is really important. When you work computationally, you have the power to do this. You have the ability to sort of customize and craft a working environment that knows something about the design problem. And I think that's really important. I think that's something that, all teams should be striving for. But as proud as I am of this work, there's a question that kept coming up over and over and over again. And this question still bothers me. And that's, is there a way to turn this into an app? Can I put it on the web? Can I make it a desktop app? Can I have it on my phone? Can I take it somewhere else? And we're gonna come back to this question. But before we answer it, I wanna dwell a little bit further on this idea of the purpose-built design environment. So in 2017, I left architecture to join WeWork, the co-working company. I joined the company research team to focus on automating parts of the design process. And WeWork is a pretty interesting place to think about design tools and to think about these purpose-built design environments, because the design problem at WeWork is extremely well defined. There is a standard spatial product, co-working space, which is, offices and common areas and conference rooms that just needs to be deployed consistently and over again to all of the buildings that WeWork leases. So, we were really interested in figuring out what parts of that process could meaningfully be automated and what things still required, human design intervention. So one of the first things I worked on was a tool for automatically laying out these offices. This work had actually already been begun before I joined by Carl Anderson and Carlo Bailey, and I sort of started building interfaces around it. But this is basically a routine for taking a shape, a polygon, and trying to fit a reasonable arrangement of desks into it. And so what we wanted to do was put this in the hands of designers, make it a real design tool. And designers at WeWork are always working in Revit, so we had to build a Revit plugin for it. And the way that we did this, we set it up so that you would basically draw these rooms, and it would run the shape of the room through the algorithm, and you could pick which of the many solutions that the algorithm came up with was best for each room, and you could just go boom, 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 click through, and it would inject the desks into the Revit model. And this was cool. People thought it was cool, but I don't think it was actually useful to people. And we were really curious to figure out why. We wanted to build tools that people would actually use that would genuinely save them time. And the feedback that we got with this exercise was basically, this isn't how I think about this design problem. This is not aligned with how I work. So we started in on some more detailed research to actually see how designers were working and try and build tools that were crafted to follow that. So we recorded designers, just recorded their screens while they were working in Revit and doing layout work. And we learned a lot from this. Several things in particular stood out. One was just a basic validation that it's worth automating offices. They constitute about 50% of the layout. And so it wasn't that we were trying to automate the wrong thing. That wasn't the reason why this wasn't saving people time. But one thing that we noticed was how much designers jump between tasks. And I think a mistake sometimes that programmers or software developers or non-designers make is thinking that designers approach a task in a very linear fashion. Like, first I'll lay out the offices, then I'll lay out the lounge, then I'll do the conference rooms. But any designer will tell you solving a layout problem means kind of thinking about everything at once and jumping back and forth between different parts of a problem or different parts of a process, because a decision in one place will have a consequence somewhere else. And this is not just true of sort of shifting between different program types. It's also true of levels of abstraction. So designers are constantly jumping between thinking about things at a low level of detail and thinking about things at a very high, broad level. So we might make a choice at a high level and then go down and resolve it in detail and discover that it doesn't work and we have to back out of that decision. Or we might make a choice at some local small scale that actually has consequences for a higher level decision. And so it's not just a matter of honing in from, from sort of rough to fine. You have to sort of enable designers to work back and forth across these levels of abstraction. And so for design tools to accommodate this kind of multi-scalar operation, I don't think we necessarily cracked the problem, but one thing that we tried was basically integrating a sort of higher level of manipulation. So the feedback we got from designers was, I don't first lay out the rooms and then I lay out the desks. I'm kind of thinking about those two levels of abstraction at the same time. So we made a tool that would allow designers not to design the polygon and then plug desks into it, but to sort of play around with subdividing the program region and then see what consequences that had for a lower level of detail. And key to the success of this, I think, is that the direct manipulation itself builds in some knowledge about how things should work. So the walls snap to being perpendicular, or they snap to columns, because we knew that when designers were going to put it in a partition, it was going to follow along the column line, and they might want to, move a door and see what consequences that had. And so, this tool allowed for iterative exploration of different design solutions at multiple levels of abstraction at once, which I think was really powerful. And this work continued beyond desk layout. This is a tool that I had started to contribute to around the time that I left WeWork, and my colleagues, Jonathan Schumacher, Leland Jobson, and Serena Lee were really heavily involved in building. And this is a tool for doing lighting layout automation. Our lighting designers were saying, we're doing the same thing over and over and over again. Can we take the spaces that are defined in Revit and automatically lay out lights the way we were doing with desks? And this thing is even cooler, I think, than the desk layout, because it also allows kind of individual manipulation of the individual elements. So, you would get an automatic solution, but then you could also go in and say, actually, I want to scooch this alignment, or I want to redistribute these, or I want to choose a different fixture type for this room. And it was very much an encapsulation of the logic of the design problem at hand, in such a way that designers could go through doing the lighting layout of an entire WeWork floor much, much faster than they could have done manually. So looking at all of this, you might come away and think, okay, maybe computation is really good for rationalizing complex form, or analyzing performance, or automating these routine repetitive tasks, or producing 1,000 WeWorks, but it will probably never be useful for problems of aesthetics or composition or truly creative design exploration. The computer will always do the boring stuff, but anything around kind of, creative or aesthetic exploration is my job, the designer. And I want to challenge that a little bit too. This thing on the screen is a 2D composition. It's, I consider it a piece of artwork, and it was generated by an algorithm. And interestingly, it was generated by the algorithm that also produced these two compositions, and also all of these compositions. I, in my spare time, really like to use Grasshopper to build these kind of like abstract art generators of one kind or another. And I think that this may seem like kind of a weird turn from the previous discussion, but I think it actually has relevance for how we think about the problems of generative and automated and parametric design, because what this is all about is generating novelty, generating like variations on an idea. But computers are really good at generating variations on a similar idea and not so great at generating new ideas altogether. And so what I find is that whenever I build one of these that generates a bunch of different options, a bunch of different iterations with the same logic, there might actually be a fair degree of variation. But after about 200 of these, maybe 500 if I'm lucky, I'm just bored of it. It's the same strategy applied over and over again. It's the same sort of family of solutions, and it's never going to break out of the limits of the logic, which is logical because that's all I've told it how to do. So, you know, I don't necessarily know what these are for, except as, you know, an exploration into that very question. I think that, you know, these generative algorithms that aren't so concerned with performance might be, you know, just inspiration tools. They, you know, they maybe give you ideas, and maybe it's up to you to interpret or turn something into like a real design strategy. And these work in 3D too. I've explored even more architectural examples, like trying to create a generator for sea ranch style houses. And, you know, I always try when I'm building these to make a script that can sort of pass what I call like an architectural Turing test, something that looks like maybe it could have been conceived by a human. But, you know, even when I start to build in a little more logic about spaces, inevitably you run into the problem of kind of bottoming out. And after a while, like all of these kind of start to look the same, and they really cease to be novel generators of new design strategies. They're really just a sort of relentless iteration over the same strategy over and over again. And the reason that I bring this up is because I think this has significant consequences for what is being discussed a lot in the industry right now, which is this idea of generative design. After a while, any given algorithm is gonna bottom out in terms of the novelty it can produce. It's gonna cease to surprise a human. And I think that's significant, because I think generative design gets talked about in this way that it's suggested that it's exploring all of the possibilities. I actually think that the first time I grabbed this slide from a marketing materials of a tech company that I won't name, I think it even said, you know, right now it says explores all the possible permutations of a solution, which is, you know, more accurate. I think at one point it even said explores all the design possibilities. And I think that that still gets implied when we talk about generative design, that like we're studying every possible iteration, when that's really not the case. But with that said, you know, this is not a bad concept. The core of generative design is that you take a system that can generate options of one kind or another, and you couple that with a way to test how good those options are. And you let the computer evolve better solutions automatically. And as long as you can build a generative strategy that, you know, actually produces a reasonable subset of the valid solutions, and you have a system that can measure things that actually matter to the design, then this is an amazing way to work. But the trouble is that both of these things are really hard. Creating really good generative routines is hard. Creating evaluative tests that actually encompass the things that we mean when we say a design is good is also really hard. On the generative side, I like to talk about this trade-off between novelty and validity. It's really easy to do what I do when I'm making my drawings, which is make a bunch of super crazy, surprising options if you don't have constraints, if you don't have some performance criteria that you need to meet, or limits on the space of what's possible. It's also easy to encompass a bunch of these, you know, design constraints and build an algorithm that produces only satisfactory solutions to that constraint space. But it's very hard to do both of these things at the same time. There's always a tension. which is not to say that it can't be done. And I want to give a lot of credit to The Living, which is part of Autodesk Research. Their research in this is really, I think, the best in the industry around actually putting this into practice on real design projects. They're really making an effort to measure things that matter, and they're really making an effort to build generative design strategies that can produce varied solutions to a given problem. And, you know, so I think this is really cool. They have a strategy that defines these neighborhoods, and it lays out the kind of groupings, and they took into account a bunch of input from the people who are going to be working in this space to develop their performance criteria. And, you know, they arrived at a better solution. And I think also, to their credit, they acknowledge the extent to which that automatic solution had to be tweaked by a human as well as a part of the design process. And that's not something we should shy away from. That's actually a critical part of the process. But the point that I want to make is that, you know, at any of these moments, the computer is not actually doing what we would call design. It's exploring the strategy that you give it. And I think most designers would look at all these options and say, yeah, these are kind of all variations on the same strategy. And I really believe that human designers effortlessly slip between these two modes, between exploring a single strategy in depth and inventing and trying different strategies. And I think most generative design kind of is only good at one of these axes, really hinges on just operating in the kind of deep exploration of a single strategy, which is sometimes totally appropriate for certain kinds of design problems. But I think, you know, Daniel Davis wrote a very incendiary article called "Generative Design is Doomed to Fail." And I know Daniel well. He's talked to us quite a bit. And, you know, I think this is one of the key things he was getting at, is not that generative design is bad, or we shouldn't do it, or it shouldn't be a part of a design process, but that it isn't in and of itself a sort of replacement for design. It doesn't actually do design. It's really just a mechanism to explore a design strategy. And that leaves it up to us designers to invent, and not only invent, but encode those strategies. If you want to partner with a generative algorithm, you have to not just come up with a strategy, but you have to figure out how to describe it as a Grasshopper script or a Dynamo script or some other piece of code. One last quick point I want to make is that our tools have led us into a state like this, where a lot of people are building similar things over and over and over again. There are a lot of stadium build generators. And I think there are two reasons for this proliferation, and one of them is very good, and one of them is bad. In my mind, the good reason for this is that people are creative. People are inventing lots of diverse strategies to attack a problem. Like, you know, the AECOM bowl generator is not going to be the same as the Lacunace bowl generator. They're going to have different strategies and different priorities and take different parameters, and that's amazing. The bad side of this is that the other reason these things proliferate is that it is more work to integrate someone else's tool than it is to build your own. I think this dates back to some of the problems I was talking about earlier with things like Grasshopper. It's very hard to share scripts, no matter how carefully you want to annotate them. And, you know, if you want to adhere to a standard, you've got to make sure that you've got the same plugins and you've got the right Rhino model set up. And, you know, there are just all of these barriers to sharing. And even if you manage to get it running, that thing may not plug in to the workflow that you're doing, the project that you're building, the stadium that you want to build, which has a different set of constraints. And so figuring out how to get all of this computational intelligence that we're giving away for free out in the world in such a way that it can play well with others. It can sort of connect and build and contribute to a sort of universe of computational intelligence is something that I think we as an industry really need to strive for. So I think I want to just sum up kind of a few of the big takeaways from everything that I've just said. What do we want as designers? What should future design environments look like? I think one thing that we want, the thing that got me hooked on Grasshopper from the beginning, is we want to automate the boring, repetitive stuff. Nobody wants to do the same thing over and over and over again. We also want to do this in purpose-built design environments that encode the problem constraints and the project goals that we're trying to solve. We want our tools to help us solve the problem. We want tools that represent more knowledge about the problem itself and actually contribute in some way to the solving of that problem. We also, I promised I'd come back to this, we want the ability to share these tools easily with others. If we create a design environment that's awesome for doing one particular task, chances are we're not the only person who wants to do that task. We want to make it available to other people. We want to have a conversation around it. We also want these tools to enable direct manipulation right alongside automation. We don't necessarily just want to run everything through sliders. Like actually getting in there is a key component of an effective computational strategy. And lastly, we want the ability to pick from among these diverse strategies and easily incorporate them into our workflow. We want to be able to rely on the generosity of others, the incredible brain trust that's out there. And right now it lives in, you know, this script that I go download from this page on the forum, or maybe if you're lucky, it's on Food for Rhino or on the Dynamo package manager, or maybe it's just some code snippet somewhere. It remains difficult to pull in other people's encoded intelligence and fold them into your workflow. So I promise I didn't come here just to give you a sales pitch, but I did say I would talk a little bit about Hypar. And the reason why I lead into this is that everything I'm saying is a big part of why and how we're building Hypar. And again, I don't think we've solved every piece of every one of these problems, obviously. But I think a lot of these challenges are the things that spurred Ian and Anthony and Matt, the creators of Hypar, to kind of start down this path. So, you know, Hypar is a web-based interface for running sort of computational logic. And so I can go on Hypar and I can grab a function that might turn the walls that I brought in from Revit into panels. And I might grab someone else's function, which turns those panels into some sort of prefabricated wall panel with framing. And so this is really about enabling you to automate the boring stuff. Like, you should be able to just drop in a model, grab it from Rhino or from Revit, and be able to utilize routines that automate the parts of this that are repetitive. We enable you on Hypar to customize your design environment with data readouts and legends and tables. This is a tool for doing like office layouts. And you know, you can rely on these existing functions. You can start to build up a design environment with legends and data readouts and all these things to kind of help you explore the design problem that you care about. You can, you know, whatever that design problem is at whatever scale, whether it's at the level of the detail of, you know, the framing in the panel, or it's the level of a master plan, if it's a panelization problem, whatever it is, there's data associated with it. And we want to make it accessible in a way that doesn't necessarily require you to write any code. So you can rely on computational routines that have been made available by the Hypar community and just plug these into your project, and then be able to sort of craft this design environment that's purpose-built to your needs. Importantly, we also support direct modeling of various kinds. I think we have a lot of work to do on taking this even further, but it is a key component of the way that we're thinking about this problem. You should be able to just get in there and draw and model as a component of a computational strategy. Like, it's not sufficient to drive everything through sliders or buttons or toggles. And, you know, this is one of the things that we encountered with Human UI a lot, is that like people just want to control everything through the UI. And I always say, no, you want to do it with Rhino plus the UI. You want to afford people the ability to interact with the modeling environment at the same time as they're interacting with the tools. You want to be able to share this stuff with anyone. So Hypar is on the cloud, which means that you can have it on a mobile device, have it on an iPad, have it on Windows, have it on Mac. Like, you can reach all of your projects, you can interact with all of the work that you've been doing in whatever context you need it, and you can easily share it with other people. It's as easy as sending a link. They don't have to download anything. They don't have to, you know, install any plugins. You know, they don't have to make sure that their file is set up exactly the right way. You know, it's really designed around the portability that modern tools around the cloud enable. things, we're already doing this with things like Google Docs and Airtable and other tools. So why can't we do it with our computational models? So to dive in a little bit more to just how this system itself works, the kind of core unit of logic in Hypar is a function. So everything you see over here on the left, each one of these rows is a function. So I have a function that I'm using now, which does a sort of view radius analysis on a mass. And that mass is generated by another function, but I could bring it in any number of ways. And that, I think, is one of the key concepts, is that, in a way, this is a computational model. It's wiring together a bunch of logic, but it doesn't involve a lot of wires and a lot of complex rigging up, because Hypar functions can describe the things that they need and the things that they produce. So when you're building a workflow on Hypar, all of the functions that are integrated just connect to each other automatically, because levels knows that it needs, or the floors knows that it needs levels, and structure knows that it needs an envelope. And because there's a way to sort of consistently describe the computational logic of each piece, it makes it really easy to swap out different strategies. So maybe I don't like this envelope strategy. Maybe I want to try somebody else's envelope strategy. Or maybe I want to build my own envelope strategy. Or maybe I just want to draw an envelope and I want to plug it into all of this computational logic. And that's really what we're trying to enable with Hypar. And the thing that we're really excited about is that a community has started to grow up around this. And people are starting to share their functions on Hypar. And you can browse through a gallery of other people's logic and just effortlessly plug it into something that you're working on. You can just drop it into your workflow. You can play around, and then you can contribute to this yourself. These functions don't have to be written in code, although they can be. We allow you to write functions in C# if you know how to do that. But they can also be Grasshopper scripts. You can take a Grasshopper script that you've already written and just plug a few things into the front and onto the back, and then publish it to Hypar and make it available for other people to use. And they don't ever have to see your spaghetti. They don't even have to see your secret sauce, how you built it. They can just use it and benefit by it. We also enable Excel-based functions. So a lot of, everybody who's done computational work on projects knows that Excel is gonna be a part of the story at some point. You're gonna be dealing with a bunch of data, or you're gonna wanna spit it out in a format that someone else can interact with, or you're gonna, just need to load in a bunch of pre-established values. And so we also support taking Excel functions and designating a few of their inputs and a few of their outputs, or a few of the cells as inputs and outputs, and running those as functions in your workflow as well. So, okay, that's the end of the sales pitch part, and actually pretty much the end of the presentation, but I just want to sum up with a few closing notes. So regardless of whether you want to use Hypar personally, and whatever your skill level is, or whatever the level of facility that your firm has with computational approaches, I think we can all strive to enhance our design environments with these basic ideas. We want to automate the boring stuff. We want to embed goals into our design environment so that they help us achieve them. We want to make our expertise accessible. And so even if you're never going to touch Hypar, please annotate your Grasshopper scripts. Please make sure that you design your computational logic in a way that someone else can pick it up and use it, or it will never grow. It will never scale. It will never really serve to change the way things are done. Draw and model as much as you script. Don't be stuck in thinking that everything has to be purely algorithmic in order to be effective. The best approach, I believe, is a hybrid approach that unites direct modeling and computational modeling working together hand in hand. Use computation to go deep and use your brain to go wide. Don't fall into the trap of thinking that a computational search is the same as a design exercise. It is perfectly good, and in fact, amazing, to utilize computation for what it's good at, which is exploring the depth of a strategy that you've defined. But it's also still up to you to come up with good strategies and come up with multiple strategies, because I've built a lot of Grasshopper scripts in my day, and I can tell you that inevitably that script had to be rewritten over and over again as I invented new strategies to solve the same problems. And finally, resist the urge to reinvent the wheel. I think we all see this in different ways at our firms. That might just be, oh, we're going to start our InDesign template from scratch every time. Or, we're gonna redefine the way that we model in Revit every single project. And I think that, designers love to do this, and I don't know what it is. I think it's this idea that you sort of like design everything around you, but some things don't need to be designed. And I think that, you know, you can really focus on the things that matter about the outcome, which is the space that you're delivering, the cities we're delivering, the, you know, the architecture that's being created. If we focus on just that rather than reinventing the wheel with all this other stuff, like, you know, you maybe don't start a stadium generator from scratch. Maybe go see if there's one out there on the internet. Maybe use the one that's on Hypar. And, you know, I think that there are ways to leverage the work that's already been done. And I think the whole industry will benefit if we get better and better about this. So that's all I have. I'm super eager to hear from you all, take your questions. Just a little bit of blatant self-promotion. You can find me on Twitter or Instagram or my website, and please follow Hypar on Twitter, Instagram, or our website. And if you're really interested in being a part of the conversation, you can find a link to our Discord community, which is where we're talking about how technologies like this are impacting the future of design practice. So yeah, that's it. Let's open it up for questions.